Something not right.
No, it's all right. What I want to look at is the connection. How is it meshed? Very poor mesh for the connection, you see?
Yes.
See this connection?
Should be smaller than that.
It should be smaller than that, yeah. So that's what you should be doing, guys. Those good guys who requires good marks, they should go and refine this. Anyway, you have to test too. Anyway, here we are, have the mesh, okay? What I will do, go to output here. Do you remember? You see this red button here? Which is select solver. You have to select the solver. I'm going to select a Fluent solver, not Ansys CFX. I'm going to select what?
Fluent.
Fluent, what is it? Fluent, FL.
No.
Fluent version 4, version 6. Okay? I don't care about the structural solver. Select anything, select Ansys, doesn't matter. But Fluent version 6, that's what I will select because that will be my solver. Okay? And say okay. Come to post-processing here. Not post-processing, come to the output. Okay, we have just done this. Do you remember this? Export. This is write an input. Save project, yes, save it. Burns, yes. Now, the file Fluent, give it a name.
Fluent.
No, what's your name?
Raj.
Raj Case. No need for chopper. No need for chopper. And say okay. And say done. Where will it save it? It save it in H, thermodynamics.
By Raj. Yeah, in user files.
Okay, now we have written, now this is when you say I have finished with this. I have written it somewhere there and I have finished with this.
To go Ansys now.
Now we will go to Ansys package. So go to all programs, Ansys,
APDL.
Fluid Dynamics. Okay, Fluent.
Okay.
And launch Fluent. Now 3D, okay. Okay. Now this is Fluent. Now other people might be looking forward to solve it with Ansys CFX. I do encourage them. Okay, but I recommend Fluent because it's more powerful. Right now, file, read, mesh. Right, and I will go to where it was stored.
My computer.
My computer.
P.
H.
Last. Terminal Raj. This. User files.
Here it is.
Yes.
And I will say okay. It will read the mesh here, guys. See the mesh? It was read. Oh, it was read by Fluent, and now you are ready to fix the boundary conditions.
So what is going to happen with the boundary conditions?
We are fixing it now.
We fix it something.
Like what is the significance of this?
Oh, you need to tell this geometry there is an air coming from here, there is fuel coming from here, and there is the products going from there. And what kind of models are you talking about?
Analyze it.
Oh, like we are setting the limits here?
We are setting the problem now. We are setting the problem, and that's why I gave you this presentation today. We need to go through it sometimes if we find the time. But please have a look at it. Right? Now, before I do anything, I will save file, write, case, and I will read. Do you want it here?
Yeah.
Rajcase.cas. I will say okay. Done. Now, the second step, I will fix the models. Here is the models which I'm going to review with you, or you have to read about them. Include multi-phase. We don't want multi-phase. Energy, you have to turn it on. You have to turn the energy on because here we have combustion. Energy is very, very important. Here is the turbulence model. You see, viscous lamina is a turbulence model. There are so many turbulence models here. You see these inviscid, laminars, polar almas, K epsilon, co omega, transport, transition SST, Reynolds stress, detached eddy simulation, large eddy simulation, a lot. I'm going for a steady calculation, and I will tell you what I mean by steady later on. K omega model. I will not mess with all this. I will accept them as they are. I went for K omega because my experience tells me that this is the most stable model, and I will say okay. Okay. Do we need to consider radiation? Any combustion, radiation in any combustion is very important, but for simplicity, I will keep it off.
What is the meaning of radiation?
Radiation, that means heat transfer by radiation. Here is the combustion. There is a fuel coming, and it will burn, right? So heat had three moods: conduction, convection, and
Radiation.
here we are mainly relying on convection.
Okay.
But radiation is very important in combustion. So I will keep it off. It won't affect the result too much. Heat exchange, I don't have any heat exchange. Species, that is where the point is. I will say edit species, and I will go for species transport, right? And I will assume volumetric reactions. Okay? And I will go for eddy dissipation model. And here I will go for, now what I want from you, some people will choose, I want them to choose methane, some heptane, some whatever hell from this hell. You see this hell? I'm sorry for the word hell. Right? So I'm going to go for methane. Do you see methane here? Do you see this one here? Methane ion. I want other people to test heptane, hexane, octane. I want you, if possible, to test more than one fuel mixture. But for simplicity, I will go for what? What is
Methane.
it? Methane ion. That is methane ion mixture. So what I did here in the model, I went for species transport, volumetric reactions, diffusion energy source. You can either collect inlet diffusion, doesn't matter so much, right? And then say apply. This is basically the combustion model. We have selected the turbulence model, and this is the combustion model. Okay? Say okay, no worries. What else? Do you want to see NOx? Are you interested in NOx, SOx, and soot?
Yes, yes.
Okay, let us get interested in next. There are three types of NOx. There is thermal NOx, prompt NOx,
Fuel NOx.
Just go for thermal NOx. Okay. Don't mess anything up and apply it. And close. Just go for one.
Okay.
Go for soot, no worries. Soot, no worries. One step. But you need fuel, CH4, oxidant, it has to be O2. You see here? You have to adjust this and say apply and say close. Discrete phase, we don't want discrete phase. We just want this mixture. And that's it. So you have set two things. You have set the turbulence model by selecting co-omega, and you have selected the combustion model by taking species transport with the actions. Now, material, you don't have to mess up with it, right? Cell zone, you don't have to. Boundary conditions. You remember air inflow? Click on it. You see here it is wall. No, it's not wall. It is velocity inlet. Change it? Yes, change it. Now, we want to change it into the velocity. We said you have to multiply. Give me your last
5.2.
5.2. So 0.52 divided by 10. Right? That is the velocity of air. Its position is in the airflow, right? K omega, this one, change this as thermokinetic energy 1 And specific dissipation rate 0.1, make it 10 times less. Thermal, leave it as it is. Radiation, forget about it. Species, it is what, guys? What are the species here? Huh? Oxygen, right? Right? Do you agree with me? Because why I have selected 0.1? Because oxygen is 21% off by volume, right?
Okay.
And then I will go, okay. Don't worry about these are fine. So species, we have only oxygen by 0.21 coming, right? This is the inflow air. Now there is inflow fuel. Again, I will change it to
Outlet.
to inlet, velocity inlet. Now, kinetic energy, this is 0.1. Now, the velocity will be 3 times, so approximately 1.56, right? In your case. Okay?
Yes.
Now, come to thermal, leave it as it is, 300 degrees centigrade radiation, don't worry about it. Species, do you remember? Do you agree with me?
Yes, we
Methane,
did.
100% methane. Right?
Yeah. The fuel.
Yeah.
Yeah.
All the fuel. Don't mess about the others. Say, okay. Do we have anything? Outlet vent, that's the best for it. Outflow. Change it to outflow. Simple as that. Nothing else. Right? So here, now, dynamic question, we don't want by dynamic. Reference values, we are happy about them. No worries. Solution method, don't mess up, leave it simple. Solution controls, if you read about them, they prefer all these ones to be, this is the relaxation factor. Change them to 0.9 rather than 1. 1 is too much. Just make them 1.9. Everything, make it 0.9. Everything 1, make it 0.9, because 1 is too much relaxation. I mean, it produces crude results. Zero point 0.9. 0.9. 0.9. 0.9. And that's it, energy 0.9. And then say okay. Monitors, forget about them. Solution initialization. Why is it hanging? Now, you need to initialize the solution. Otherwise, nothing will take place. So, click on initialize. Just click on it, and it will take a bit of time to tell you it has initialized. And then, calculation activities, run calculations, number of iteration, make them 1000 or 2500. Okay, and let it report to you, and then tell it to calculate. Either broke down or it went forward. So you can see reverse flow in what? There is a reverse flow from the out flow, rather than going out, it's going in. But this is because this is the initial situation. Eventually it will settle down. So let it run. Let it run for a while. Right? So that's what I want you to train on. You see the number started decreasing, eventually they will disappear. This is how to run the simulation from the mesh. What I want you to do is to try to run the simulation during this week. Okay? Some of you have screened this, and some of you know it's better than others. Try to do it in a teamwork, please. Don't do it alone. Now, so you can see the CO2, the NO, and the soot. It reports you about all these species involved,
It's done.
right? Sorry?
It's done.
Reverse law in one. And eventually it will settle now. There is no any more reverse law. So now eventually it will run smooth without any problem. Okay, so I want some of you to test different fuel space, but all of you test
करते हैं इसको.
methane mixture first, and then if you can do another fuel, that will be great. Right, now can I ask all of you to start engaged with it
So that
in
this
half
this
an
is
hour
it?
to see? Yeah, that's it.
Oh.
This is running.
All
No,
right.
no. The results are yet far away. We don't know.
But no more operations to be done.
No, there is analysis.
Oh, right.
You need to analyze the results.
So are we going to compare them?
I want you to run now. Forget about now. Run. Right? Run it, and then we will come to that next week. I want you to be able to run